So, as I've said, first things first, we need to focus on the physical chemical properties of alkanes and alkenes, and what makes them special and what is their specialty. As you know, alkanes are made up of two sp2 hybridized carbon atoms. What does that mean? We discussed this in the introduction, or our recap, and we saw that sp2 hybridized carbon atoms have 3 sp2 carbon atoms, each with this angle of 120 degrees between them. And perpendicular to that, we have one leftover p orbital. And these orbitals can now form bonds. And we can see this here. So we see here our two carbon atoms. And first, the two of the sp2 orbitals that are pointing towards each other, so along the axis of the two carbon atoms, they form a sigma bond. So they just overlap as you would normally expect it, and as you also know from the, for example, standard carbon-hydrogen bonds. But on top of that, we also have these two pi orbitals that were perpendicular to the sp2 orbitals. And they can now also overlap, but not along the axis, but above the axis and below the axis. And they also overlap and they form a so-called pi bond. And the bond energy of these two bonds is now different. You can see that here on this slide. So the sigma bond has a bond energy of roughly 350 kilojoules per mole. And the pi bond is a little bit weaker. It only has like a bond energy of 260 kilojoules per mole. And of course, this alters the reactivity. What is a little bit misleading is when you draw the Lewis structure of an alkene, you just draw two lines between the carbon atoms, and this can give you the feeling that that the two bonds are equal, but actually they are not. They have different bond energies and also different reactivities. And most of the reactivities that we are going to discuss, actually not just most of them, all of them are somehow interacting or working on the electron density of this pi bond, because this pi bond now has the electron density above and below, and because all of these substituents are in the plane of the sigma bond, this pi electron density is freely accessible, or more or less freely accessible to, for example, electrophiles, and they can interact with that and then, of course, start certain reactions. And if we have a look again on the alkenes, we see that they are made up of sp hybridized carbon atoms, and they have, as you remember, these sp hybridized orbitals. They have like a bond angle of 180 degrees. So two of these orbitals again form a sigma bond, but now we are not left with just one p orbital that's perpendicular, but we have two p orbitals, and they are basically forming they are both perpendicular to the sigma bond, but also perpendicular to each other. And so we have, for an alkene, we have actually two pi bonds that are formed. One is above the sigma bond, and one is basically in front and in the back of the sigma bond. So we have like electron density all around the sigma bond. And this, of course, basically means that they show the same reactivity as alkenes. Of course, some differences apply here, but overall, they are quite similar in reactivity.